Imagine this. It's 2:13 a.m. A company's entire network is silent, the office lights are off, and the world outside is asleep. But inside the server room, something is moving, not physically, digitally. A silent scan is crawling through every open port, every forgotten service, every outdated system. It's not making noise. It's not breaking anything. It's simply looking, searching, mapping weaknesses like a predator studying its prey. Now here's the twist. This scan wasn't launched by a hacker. It was launched by the company itself. Because in cybersecurity, the most dangerous vulnerabilities are the ones you don't even know exist. Welcome to vulnerability scanning, the art and science of discovering weaknesses before attackers do. In this module of ethical hacking and penetration testing, we're diving deep into one of the most misunderstood yet most critical phases of cybersecurity: vulnerability scanning. Most people think hacking begins with exploitation, breaking into systems, bypassing firewalls, cracking passwords. But in reality, hacking begins with visibility. You cannot attack what you cannot see, and you cannot defend what you do not understand. Vulnerability scanning is the flashlight in a dark room. It reveals the cracks, the weak doors, the forgotten windows, the outdated locks, and the hidden entry points that attackers love to exploit. But here's the catch. A vulnerability scanner is not a magic tool. It's not a one-click fix. It's not a replacement for penetration testing, and it's definitely not a guarantee of security. It is a diagnostic tool, like an X-ray or MRI. It shows you what's wrong, but it doesn't fix it for you. In this video, we're going to break down vulnerability scanning in a way that's cinematic, practical, and deeply educational. You'll understand not just what it is, but why it matters, how it works, where it fits in the hacking lifecycle, and how companies can use it to stay ahead of attackers. By the end of this video, you'll think about cybersecurity in a completely new way. Imagine you're buying a used car. You don't just look at the paint and the seats. You check the engine, the brakes, the tires, the wiring, the battery, the oil levels, everything that could fail. A vulnerability scan is the same thing, but for digital systems. It is an automated process that examines computers, servers, networks, applications, cloud environments, and even IoT devices to identify weak configurations, missing patches, outdated software, misconfigured firewalls, open ports, dangerous services, known vulnerabilities, security loopholes, exposure points, compliance issues. Think of it as a health checkup for your entire digital infrastructure. Just like a doctor uses machines to detect early signs of disease, cybersecurity teams use vulnerability scanners to detect early signs of cyber risk. Let's go back in time for a moment. Case study: the Equifax breach, 2017. One of the largest data breaches in history happened because of a single unpatched vulnerability in Apache Struts, a web application framework. The vulnerability was publicly known. A patch was available. Security teams were aware of it, but the company failed to scan and detect that one system was still vulnerable. The result? 147 million people affected, social security numbers leaked, financial data exposed, $700 million in fines, permanent damage to reputation, all because of one missing patch. This is why vulnerability scanning exists. Not to impress auditors, not to tick compliance boxes, but to prevent disasters. Let's break it down like a movie scene. Step 1. Discovery. The scanner begins by identifying all assets in the environment. It's like turning on the lights in a warehouse and seeing every box, every shelf, every corner. It discovers IP addresses, devices, operating systems, applications, services, ports, cloud resources, containers, databases. This step alone often shocks companies. They realize they have systems they didn't even know existed. Step 2. Enumeration. Now the scanner gets closer. It checks versions, configurations, running services, and system details. It's like opening each box in the warehouse and checking what's inside. Step 3. Vulnerability matching. The scanner compares the discovered information with massive vulnerability databases, such as NVD, National Vulnerability Database, CVE, Common Vulnerabilities and Exposures, Vendor Advisories, Exploit Databases, Security Bulletins. This is where the scanner says, this version of Apache has a known vulnerability. This Windows server is missing a critical patch. This port is exposing a dangerous service. Step 4. Risk scoring. Each vulnerability is assigned a severity score using CVSS, Common Vulnerability Scoring System. It tells you how dangerous the vulnerability is, how easy it is to exploit, how much damage it can cause, whether it is actively exploited in the wild. Step 5. Reporting. Finally, the scanner generates a detailed report that includes vulnerabilities found, severity levels, affected systems, recommended fixes, compliance gaps, risk summaries. This report becomes the foundation for remediation. Types of vulnerability scanning explained with real-world analogies. 1. Network vulnerability scanning, analogy, checking all doors and windows of a building. It scans routers, switches, firewalls, servers, endpoints, IoT devices. It looks for open ports, weak services, outdated firmware, and misconfigurations. Web application vulnerability scanning can be compared to testing every button, form, and input field on a website. Its goal is to detect issues such as SQL injection, XSS, CSRF, broken authentication, insecure cookies, and misconfigured headers. Tools like Burp Suite and OWASP Zap dominate the area of web application vulnerability scanning, making them go-to choices for many security professionals who want to find and fix issues in websites. Cloud vulnerability scanning is like checking if your house keys are accidentally left outside. Cloud misconfigurations are among the biggest causes of breaches today. Scanners examine S3 bucket permissions, IAM roles, security groups, public exposure risks, and encryption settings. Container vulnerability scanning is like checking if the ingredients in your recipe are expired. Containers often use outdated base images. Scanners find vulnerabilities inside Docker images and Kubernetes clusters to keep environments secure. Credentialed authenticated scanning is like inspecting a house from the inside. The scanner logs in with credentials and checks things like patch levels, registry settings, file permissions, and overall system configurations, resulting in much more accurate assessments. Non-credentialed unauthenticated scanning is like inspecting a house from the outside. This shows what an attacker sees, but with limited visibility. It's useful for understanding which vulnerabilities are exposed to the world. Nessus, the detective. Nessus is like a highly experienced detective who knows every trick in the book. It has one of the largest vulnerability databases and is widely used in enterprises. OpenVAS, the open source guardian. OpenVAS is powerful, free, and community-driven. It's like a neighborhood watch group that constantly updates itself to stay prepared. Qualys, the cloud inspector. Qualys is cloud-based and scans everything from endpoints to cloud workloads. It's like having a drone that surveys your entire digital landscape for vulnerabilities. Rapid7 Nexpose, the risk analyst. Nexpose focuses heavily on risk scoring and prioritization. It's like a consultant who tells you not just what's wrong, but what you should fix first for the greatest impact. Burp Suite, the web app hunter. Burp Suite is the king of web application scanning. It's like a magnifying glass that reveals every hidden flaw or bug within a website, making it invaluable for web security. Nmap is the recon specialist. Nmap is not a vulnerability scanner by itself, but it's used to discover open ports and services. It's like a scout that maps the battlefield before the main attack begins. Most people imagine vulnerability scanners as magical boxes that somehow know everything, but the truth is far more fascinating and far more technical. Let's open the scanner's brain and see what's happening inside. Fingerprinting. The scanner identifies the target's identity. Before a scanner can detect vulnerabilities, it must first understand what it is scanning. This process of discovery is known as fingerprinting. The scanner tries to determine operating system, kernel version, installed software, running services, open ports, web server type, database type, SSL, TLS configuration, application frameworks, cloud provider, container base image. It does this using techniques like banner grabbing, packet analysis, protocol negotiation, TLS handshake inspection, service probing, HTTP header analysis. It's like a doctor identifying the patient before diagnosing the illness. Every vulnerability scanner contains thousands of plugins or checks. Each plugin is a small script that tests for a specific vulnerability. For example, plugin 19506 checks for outdated OpenSSL. Plugin 51192 checks for Apache Struts RCE. Plugin 1001 checks for SMBv1 exposure. Plugin 33851 checks for weak SSH ciphers. These plugins are updated daily, sometimes hourly, because new vulnerabilities appear constantly. Scanners use two types of tests: safe checks. These tests do not exploit vulnerabilities. They only check versions, configurations, and signatures. Example, if Apache version equals X and X is vulnerable, mark it as vulnerable. Aggressive checks. These tests attempt to exploit the vulnerability in a controlled manner. Example, sending a specially crafted payload to confirm SQL injection. Aggressive checks are more accurate but can crash systems, restart services, cause performance issues. This is why companies must schedule scans carefully. After running thousands of checks, the scanner must remove duplicates, correlate related vulnerabilities, group findings by asset, prioritize based on severity. This is where the scanner transforms raw data into actionable intelligence. CVSS, Common Vulnerability Scoring System, is the global standard for rating vulnerabilities. Scores range from 0.0 to 10.0. But what do these numbers actually mean? Let's break it down with cinematic clarity. CVSS 10.0, the digital nuclear bomb. Example, Eternal Blue, MS17010. This vulnerability allowed remote code execution on Windows machines without authentication. Impact enabled the WannaCry ransomware outbreak, crippled hospitals, banks, and governments, caused billions in damages. A CVSS 10.0 vulnerability means no authentication required, no user interaction needed, full system compromise possible, exploitable remotely, high likelihood of active exploitation. This is the kind of vulnerability that keeps CISOs awake at night. CVSS 9.0 to 9.9, critical, highly exploitable flaws. Example, Log4 shell, CVE 2021-4428. A single string in a log file could compromise entire servers. Impact, affected millions of systems, exploited globally within hours, required emergency patching. These vulnerabilities demand immediate action. CVSS 7.0 to 8.9, high severity. Example, a SQL injection vulnerability that requires authentication. Still dangerous, but harder to exploit. CVSS 4.0, 6.9, medium severity. Example, a misconfigured header that exposes information but doesn't allow direct compromise. CVSS 0.1 to 3.9, low severity. Example, a server revealing its version number. Not dangerous alone, but useful for attackers during reconnaissance. A major hospital ran a vulnerability scan. The report flagged outdated Windows servers, weak SMB configurations, missing patches. But the IT team ignored the report because everything was working fine. 2 months later, ransomware hit. Patient records encrypted, surgeries delayed, emergency rooms shut down, millions lost. The vulnerability scanner predicted the attack, but no one acted. A financial institution ran an aggressive scan during business hours. The scanner attempted to exploit a known vulnerability in a legacy system. The system crashed. ATMs stopped working. Online banking went offline. Customers panicked. Lesson: scanning is powerful, but must be controlled. A small startup used OpenVAS weekly. One day, the scanner detected a critical RCE vulnerability in their web server, a misconfigured S3 bucket, and an exposed API endpoint. They fixed everything within 24 hours. A week later, the same vulnerabilities were being actively exploited worldwide. Their scanning discipline saved the company. False positives. The scanner cries wolf. A false positive is when the scanner reports a vulnerability that doesn't actually exist. This wastes time and resources. Example: scanner says SQL injection detected, but it's just a false alarm caused by a WAF response. False negatives. The silent killer. A false negative is when the scanner misses a real vulnerability. This is far more dangerous. Example: a custom web application with a unique vulnerability that scanners don't recognize. This is why penetration testing is still essential. Let's be clear. Hackers use the same tools as ethical hackers, but with different intentions. Hackers use scanning to identify weak targets, find outdated systems, detect exposed services, map attack surfaces, prioritize easy victims, automate exploitation. Tools like Nmap, Mascan, Nessus, pirated versions, OpenVAS, Shodan, and Census are used to scan the entire internet. Example: a hacker scans 10,000 IPs, finds 200 with SMB-v1 enabled, runs Eternal Blue exploit, gets access to 150 machines. This is why companies must scan themselves before attackers do.
There is no universal rule, but here's the practical breakdown. 1. Continuous scanning, ideal for large enterprises. Automated real-time scanning of cloud, endpoints, and containers. 2. Weekly scanning, most common. Detects new vulnerabilities quickly. 3. Monthly scanning, minimum requirement, often used for compliance. 4. On-demand scanning, triggered when new systems are deployed, major patches are released, security incidents occur, or new vulnerabilities emerge. 5. After every change, any update, migration, or configuration change should be followed by a scan. Part 3. Best practices, report interpretation, prioritization, patch management, SIEM, SOAR, compliance, and building a vulnerability management program. A vulnerability scan or report can feel overwhelming the first time you see it. It's like receiving a 200-page medical report filled with technical terms, severity scores, and cryptic descriptions. But once you understand how to read it, the report becomes one of the most powerful tools in cybersecurity. Let's break it down like a guided walkthrough. 1. Executive summary, the bird's eye view. This section is designed for leadership, CISOs, CTOs, managers. It summarizes total vulnerabilities, critical vulnerabilities, high, medium, low counts, trend comparison with previous scans, overall risk posture, top affected systems. Think of it as the health dashboard of your entire digital environment. 2. Asset breakdown, which systems are in trouble. This section lists every system scanned and shows number of vulnerabilities, severity distribution, operating system, IP address, business criticality. This helps teams prioritize based on impact. Example: a vulnerability on a public-facing web server is far more dangerous than the same vulnerability on an isolated test machine. 3. Vulnerability details, the heart of the report. Each vulnerability entry typically includes vulnerability name, example, Apache Log4j remote code execution, CVE ID, like CVE 2021-44228, CVSS score, description, affected systems, proof of detection, remediation steps, references. This section is where security engineers spend most of their time. SOAR, risk prioritization, what to fix first. Not all vulnerabilities are equal. Some are urgent, some are dangerous, but not actively exploited. Some are low risk and can wait. The report usually includes exploit availability, attack vector, impact on confidentiality, integrity, availability, business criticality, exposure level, internal versus external. This helps teams decide what to fix immediately. Section 13, Vulnerability Prioritization, the art of fixing what matters most. Fixing vulnerabilities is not about fixing everything. It's about fixing the right things at the right time. Let's break down the prioritization strategy used by top cybersecurity teams. 1. Prioritize based on severity, CVSS score. Critical and high vulnerabilities should be addressed first, but severity alone is not enough. 2. Prioritize based on exploit availability. A vulnerability with a public exploit is far more dangerous. Example, if Metasploit has a module for it, attackers will use it. 3. Prioritize based on exposure. External-facing systems are the highest priority. Example, a critical vulnerability on an internal printer is less urgent than a medium vulnerability on a public web server. 4. Prioritize based on business impact. Systems that support finance, customer data, healthcare, manufacturing, critical operations must be protected first. 5. Prioritize based on attack path. Some vulnerabilities act as stepping stones. Example, a low-severity vulnerability that allows privilege escalation might be more dangerous than a high-severity vulnerability that requires local access. 6. Prioritize based on asset value. Not all systems are equal. Example, a vulnerability on a CEO's laptop is more critical than the same vulnerability on a test machine. Section 14. Patch management, the backbone of vulnerability remediation. Patching is one of the most important and most challenging parts of cybersecurity. Let's break it down like a real-world workflow. 1. Patch identification. Once vulnerabilities are detected, the next step is identifying the correct patches. Sources include vendor advisories, Microsoft Patch Tuesday, Linux distribution updates, cloud provider updates, application vendor updates. 2. Patch testing, the safety net. Never deploy patches directly to production. Why? Because patches can break applications, cause downtime, create compatibility issues, trigger unexpected behavior. Testing ensures stability. 3. Patch deployment. Once tested, patches are deployed using SCCM, WSUS, Intune, Ansible, Puppet, Chef, cloud patching tools. Deployment must be scheduled to minimize downtime. 4. Verification. After deployment, teams must verify. Patch installed successfully. Vulnerability is resolved. No new issues were introduced. This is where rescanning becomes essential. 5. Documentation. Every patch cycle must be documented for compliance, audits, internal tracking, incident response. Section 15. Integrating vulnerability scanning with SIEM and SOAR. Modern cybersecurity is not about isolated tools. It's about integrated ecosystems. Let's explore how vulnerability scanning fits into SIEM and SOAR. SIEM integration, security information and event management. A SIEM collects logs from firewalls, servers, applications, cloud services, endpoints, identity systems. When vulnerability data is integrated into SIEM, alerts become more accurate, threat detection becomes smarter, incident response becomes faster, risk scoring becomes contextual. Example, if a server has a critical vulnerability and unusual login attempts, the SIEM can raise a high-priority alert. SOAR integration, security orchestration, automation and response. SOAR platforms automate security workflows. When integrated with vulnerability scanners, SOAR can automatically assign remediation tasks, trigger patching workflows, notify system owners, escalate critical vulnerabilities, generate compliance reports, launch automated rescans. This reduces manual workload and speeds up remediation. Section 16. Compliance frameworks and vulnerability scanning requirements. Many industries are legally required to perform vulnerability scanning. Let's break down the major frameworks. PCI DSS, Payment Card Industry Data Security Standard, requires quarterly external scans, annual internal scans, scans after major changes, approved scanning vendors, ASVs, used by banks, payment processors, and e-commerce. HIPAA, Healthcare, requires regular vulnerability assessments, risk analysis, patch management, documentation, used by hospitals, clinics, and healthcare providers. ISO 27001 requires continuous vulnerability management, risk-based remediation, documentation, and audits, used globally across industries. NIST 800-53 and 800-171 require vulnerability scanning, configuration management, patch management, continuous monitoring, used by government agencies and contractors. GDPR Europe requires security by design, regular assessments, protection of personal data, vulnerability scanning supports compliance. Section 17. Building a complete vulnerability management program, step by step. A vulnerability scan is just one piece of the puzzle. A full vulnerability management program is a structured, repeatable, measurable process. Let's build it step by step. Step 1. Asset inventory. You cannot protect what you don't know exists. This includes servers, endpoints, cloud resources, containers, databases, applications, IoT devices. Step 2. Vulnerability scanning strategy. Define scan frequency, scan types, tools, scope, exclusions, aggressive versus safe checks. Step 3. Risk prioritization framework. Use CVSS, exploit availability, business impact, exposure level, asset criticality. Step 4. Remediation workflow. Define who fixes what, how patches are tested, how patches are deployed, how issues are escalated, how deadlines are enforced. Step 5. Verification and rescanning. Ensure vulnerabilities are actually fixed. Step 6. Reporting and metrics. Track mean time to remediation, MTTR, vulnerability trends, patch compliance, risk reduction. Step 7. Continuous improvement. Cybersecurity is never done. Evolve. Systems change. New vulnerabilities appear daily. A mature program adapts continuously. Most people think vulnerability scanning is just run a tool and get a report. But advanced scanning goes far deeper, into the layers of modern infrastructure, automation pipelines, and real-time threat intelligence. Let's explore the advanced techniques used by top cybersecurity teams and ethical hackers. Agent-based scanning installs a lightweight agent directly on the system. This allows deep inspection of system files, real-time vulnerability detection, continuous monitoring, offline scanning, and accurate patch verification. Imagine having a security guard inside every machine instead of checking from outside. Modern applications rely heavily on APIs. API scanning checks for authentication flaws, rate limit bypasses, broken object-level authorization, injection flaws, misconfigured tokens, and sensitive data exposure. This is essential for mobile apps, SaaS platforms, and microservices. Instead of giving scanners full admin access, Companies now use role-based access, read-only credentials, and scoped permissions. This reduces risk while maintaining accuracy. Instead of scanning everything every time, differential scanning focuses on new assets, changed configurations, updated software, and newly discovered vulnerabilities. This reduces load and speeds up detection. Scanners integrate with exploit databases, dark web monitoring, threat feeds, zero-day alerts, and malware campaigns. This allows companies to prioritize vulnerabilities that attackers are actively exploiting. Modern scanners use machine learning to reduce false positives, predict exploitability, identify unusual patterns, detect misconfigurations, and analyze large environments. This is the future of vulnerability detection. Cloud environments introduce new challenges. Traditional scanning methods don't always work because cloud systems are dynamic, auto-scaling, distributed, API-driven, and multi-tenant. Let's break down how scanning works in the cloud. AWS environments require scanning of EC2 instances, S3 buckets, IAM roles, security groups, Lambda functions, RDS databases, EKS clusters, and CloudTrail logs. Common issues include public S3 buckets, over-permissive IAM policies, open security groups, unencrypted volumes, and outdated AMIs. AWS also provides native tools like Inspector, GuardDuty, and Security Hub. Azure vulnerability scanning includes scanning for issues in virtual machines, @services, Key Vault, Azure SQL, storage accounts, and Azure Kubernetes Service, AKS clusters. These services are often targeted for misconfigurations and vulnerabilities if not properly secured. Common problems detected during Azure scanning include misconfigured network security groups, NSGs, storage accounts that are publicly exposed to the internet, weak identity and access configurations, and outdated VM images. These risks can lead to data breaches if not quickly addressed. Azure Defender integrates with Azure vulnerability scanning workflows, providing automatic and continuous security monitoring across all supported cloud assets and configurations. GCP vulnerability scanning targets multiple resources, including compute engine instances, cloud storage buckets, identity and access management, IAM, Google Kubernetes Engine, GKE clusters, and cloud functions. Frequent GCP misconfigurations involve public cloud storage buckets, weak service accounts, exposed application programming interfaces, APIs, and firewall rules that are not properly secured, potentially allowing unauthorized access. Most cloud breaches happen not because of software vulnerabilities, but due to misconfigured permissions, public exposure of resources, weak identity controls, lack of encryption, and insufficient logging. These factors make configuration analysis crucial in cloud security. Because misconfigurations top the list of breach causes, cloud security scanning focuses heavily on analyzing configurations rather than only checking for code vulnerabilities. This proactive analysis helps reduce risks from human errors and oversights. Containers and Kubernetes have transformed modern infrastructure, enabling scalable deployment and management of applications. However, they also introduce new security risks and require specialized vulnerability scanning practices. Before deploying a container, it's vital to scan its image for outdated software libraries, vulnerable packages, unsafe dependencies, misconfigured base images, and hard-coded secrets. This ensures threats are caught before reaching production. For example, a Docker image built on Ubuntu 16.04 could contain hundreds of outdated packages, creating multiple entry points for attackers. Scanning identifies and flags these risks before containers are used. Once containers are running, scanners monitor for privilege escalation risks, insecure mounts, exposed network sockets, dangerous capabilities, and deviations from the original image to ensure runtime security. Kubernetes environments face risks like exposed dashboards, weak role-based access control, RBAC, insecure pod configurations, privileged containers, unsafe network policies, and poorly configured admission controllers. Security tools such as KubeBench, KubeHunter, and Trivy are essential for scanning Kubernetes clusters, detecting vulnerabilities, and ensuring best security practices are followed. Modern companies using DevOps and CI/CD pipelines deploy code daily, sometimes hundreds of times a day. This rapid deployment means vulnerabilities can be introduced at any moment during the development lifecycle. To address this challenge, shift-left security has become essential. This approach embeds security scanning early into the development process to catch vulnerabilities before code reaches production environments. In pre-commit scanning, before developers push code, tools check for hard-coded passwords, API keys, secrets, and vulnerable dependencies. This step prevents sensitive data exposure and keeps the codebase safer. During CI/CD build time, scanners inspect dependencies, software libraries, container images, and infrastructure as code templates for vulnerabilities. This step ensures security issues are caught as part of the automated build pipeline. Before deploying to production, deployment time scanning validates configurations, permissions, network exposure, and secrets management settings. This important step ensures major misconfigurations do not reach live environments. Even after code is deployed, continuous scanning in production is vital. It detects new vulnerabilities, identifies drift from secure baselines, catches misconfigurations, and ensures ongoing compliance throughout the system's lifecycle. Ethical hackers don't just run a scanner. They use scanning strategically as part of a larger attack chain. Let's walk through the ethical hacker workflow. Reconnaissance. Before scanning, ethical hackers gather IP ranges, domains, subdomains, technologies, cloud providers, exposed services. This ensures scanning is targeted and efficient. 2. Initial scanning. Ethical hackers use Nmap, masscan, russcan to identify open ports, running services, operating systems, application versions. This forms the foundation for deeper scanning. 3. Vulnerability scanning. Tools like Nessus, OpenVAS, and Qualys are used to identify known vulnerabilities, misconfigurations, weak services, outdated software. 4. Manual validation. Ethical hackers manually verify false positives, exploitability, attack paths. This is where skill matters. 5. Exploitation, if allowed. If the scope permits, ethical hackers attempt privilege escalation, lateral movement, data access, persistence. This shows the real impact of vulnerabilities. 6. Reporting. Ethical hackers provide detailed findings, proof of exploitation, business impact, remediation guidance. This is the most valuable part of the engagement. Manual vulnerability management is slow and error-prone. Modern companies automate everything. Let's explore how. Automated scanning schedules. Scanners run daily, weekly, after deployments, after configuration changes. This ensures continuous visibility. 2. Automated ticketing. When a vulnerability is detected, a ticket is created, assigned to the right team, prioritized automatically, tracked until resolved. This eliminates delays. 3. Automated patch deployment. For certain systems, patches can be deployed automatically. Example, browsers, operating systems, cloud workloads, containers. 4. Automated rescanning. After patches are applied, scanners automatically verify. Vulnerability is fixed, no new issues were introduced. 5. Automated reporting. Dashboards show risk trends, compliance status, remediation progress, vulnerability heat maps. This helps leadership make informed decisions. Cybersecurity evolves rapidly. Here's what the future holds. 1. AI-driven vulnerability prediction. AI will predict vulnerabilities before they are discovered publicly. 2. Autonomous remediation. Systems will fix themselves without human intervention. Zero Trust integrated scanning. Scanning will become part of identity-driven access control. 4. Real-time cloud drift detection. Systems will detect misconfigurations the moment they occur. 5. Continuous API security. API scanning will become as common as network scanning. 6. Quantum era vulnerability models. New cryptographic vulnerabilities will emerge as quantum computing advances. Let's bring everything together. Imagine your digital environment as a massive city. Servers are buildings. Applications are roads. Users are citizens. Data is the lifeblood, flowing through every street. Now imagine that somewhere in this city, a door is unlocked, a window is cracked open. A forgotten alley leads straight into the heart of your infrastructure. Attackers don't break in by force. They walk through the doors you didn't know were open. Vulnerability scanning is the act of walking through your city with a flashlight, checking every door, every window, every alley, every rooftop. It's not glamorous, it's not dramatic, but it is essential. Because the greatest cyber attacks in history didn't happen because attackers were brilliant. They happened because defenders were unaware. Vulnerability scanning turns the unknown into the known. It transforms darkness into visibility. It gives companies the power to fix weaknesses before attackers exploit them. And in a world where cyber threats evolve every second, visibility is not optional. It is survival. If you learned something powerful today, if you now understand vulnerability scanning in a way most people never will, if you want more cinematic, deeply educational cybersecurity content, then hit like, subscribe, and turn on notifications for Knowitrix. Because this channel isn't just about teaching cybersecurity, it's about building the next generation of ethical hackers, defenders, and digital warriors. And you, yes you, are now one step closer to becoming one of them. Stay curious, stay sharp, stay secure. This is Knowitrix, signing off.